Okay, now we are going to look into the next concept, that is the application of the fixed second. Okay, so till now we have learned about the fixed second law, that it holds true for your unsteady state diffusion. And as per the solution of the fixed second law, it can be given by this expression, right? Where C x comma t basically tells us about the concentration at a particular position with respect to your time. And A and B are the constant value. And there is an error function which we have discussed earlier, which basically includes your position. And D is your diffusivity, and T is the time that is taken for the diffusion to take place. Okay. Now, in the application of the fixed second law, this condition holds true for various different applications. This is actually the real case scenario that occurs in your environment. Okay, but as per our syllabus, we will mainly be looking into three major applications. That is your carburization, your decarburization, and alloy coupling. Okay, so these are the three applications which we will be learning in your fixed second. Okay, so we'll be discussing about all these three applications. What is carburization? What is decarburization? What is alloy coupling? And we'll derive what is the solution for all of these expressions, all of these applications. Okay, so let us start with your carburization. Let us see what happens in case of your carburization. Okay, so the very first topic will be your carburization. All right. So in case of carburization, it is a very simple concept. What you need to understand that for low steel components, if I have a low steel component, for example, various industries use different components of your steel, right? For example, in case of your gears, in case of your mechanical instruments, which basically undergo your wear and tear deformation, the carburization plays a very important role. Carburization is basically a technique in which we increase the hardness of the surface. Okay. For example, if I have a mechanical gear, so you must have seen the mechanical gears. These are like this. These are the teeth of your gears. Okay. And mainly they undergo deformation like this. Okay. So what will happen? The teeth of the gears, these are the different gears which undergo your different revolution inside each other. And because of that, there are chances of the wear and tear to occur because of the friction. Right now, it is very important that the hardness of the surface is quite large. Okay. In carburization, it is basically a surface hardening technique where we diffuse carbon over the surface, and because of that, what happens in case of your carbon diffusion? It basically pins down your dislocation movement, giving the strength or giving the hardness of the surface. Okay, so if I define your carburization, you can simply write that carburization is a technique of surface treatment, is a technique of surface treatment of surface treatment where carbon is diffused, where carbon is diffused, where carbon is diffused into the steel component, into the steel component, increasing the strength of the surface, increasing the strength of the surface. increasing the strength of the surface. Okay, so how this carburization mainly done is what we are going to understand, and based upon that, we will see that how this carburization is applicable, means how the fixed second law is applicable for the carburization part, and what is the solution for the fixed second law for the carburization. Okay, so what we need to understand that carburization mainly holds true for your low steel components. Okay, it is basically done for your low steel components. What are your low steel components? Those steel components which contain less amount of carbon. For example, the carbon should be less than 0.258%. Okay, such components are basically known as your low carbon steel components. Okay, and in this carburization plays an important role. So how is this carburization mainly carried out? Okay, in order to understand that, let us take a block of steel. Okay, low carbon steel block, and let us understand how the carburization takes place. Okay. So we know that the carburization is a surface technique, right? So if I take a low carbon steel block, say the initial composition or the initial concentration of carbon in this steel block, let me consider this to be C. Okay. So what we do, we take this steel block and we keep it inside a carburizing medium. Okay. So it is kept inside a carburizing medium. Okay. So this is my carburizing medium. Having the concentration, let me take the concentration as CS. Okay, so the carburizing medium has the concentration of CS. Okay, now definitely the CS is greater than C. The concentration of the carbon present in the carburizing medium is greater as compared to the concentration of carbon in your steel. Okay, now if I heat this complete system, what will happen? Basically, if I provide heat to this system, the temperature of the system is going to increase, right? So what will happen? There is a difference of concentration that is created between your carburizing medium and the steel, right? And why is that so? Because of the difference in the concentration of carbon in the two mediums, right? So what will happen? The carbon from your carburizing medium, it will start diffusing. The carbon will start diffusing from all the different directions. Okay. Now, what will happen? Basically, with the increase in the concentration of the carbon inside your steel block from the surface, the hardness of the surface is going to increase. And this particular process is known as the carburization. Okay. So we know that with the increase in the concentration of carbon, the dislocation is difficult. It is getting difficult to move over the surface, and therefore the hardness of the surface increases. So this is the basic concept behind your carburization and how it takes place. And we can say that diffusion plays an important role for the carburization to occur. Okay. Now it is an unsteady state diffusion. Why is that an unsteady state diffusion? Basically, because the concentration of the carburizing medium is fixed. First of all, we need to understand that. Okay. The amount of carbon that is present in the carburizing medium, it is not infinite. It has a particular concentration. Okay. That is CS in this case. Okay. Moreover, with respect to the time, the amount of carbon that is diffusing through the surface, it increases everywhere. Okay, so it is basically a kind of an unsteady state diffusion. Unsteady state diffusion. And therefore, I can say that your fixed second law is applicable for this case, and the solution of the fixed second law, that is Cx comma d, is equal to a plus b error function x by under root 4 dt can be applied for this condition. Okay. So in order to understand the solution for the carburization part, we first of all need to remove this A and B with the concentration values, right? So our objective to find the solution will basically by removing this A and B values, and based upon that, we will determine what is the solution for the carburization. Okay. Now, in order to do so, we need two different conditions, right? We have two different variables, so we two different constants. So we need two different conditions for that. Okay. So our very first condition will be the boundary condition that is occurring at the boundary. Okay. So this side is your carburizing medium, and this side is your steel component. Okay. So our very first condition will be my boundary condition. Okay. So let us see what is this boundary condition and what happens in this case. Okay. So before understanding this boundary condition, we first of all need to draw the graph that how the carbon is moving from the carburizing medium to the steel component. Then it will be much easier to understand the boundary and the other conditions. Right. So if I draw the graph that is happening over the surface, okay, I'm just drawing this part in a larger format. Okay. All right. So say this is my concentration. We'll see how the concentration varies in case of your carburization. And so this will be my position. Okay. So say this is my x equal to 0. That is my boundary. Okay. Now what you need to understand that the right hand side of my boundary, it mainly contains your carburizing medium and it has a higher concentration of CS, right? So let us consider that the concentration is higher and this is the concentration as CS. Now this is constant throughout the carburizing medium, right? Everywhere inside my carburizing medium, I can say that the concentration remains constant as CS. Okay, so this is at P equal to 0. That is the initial. Okay. Similarly, if I look into the concentration of the steel component that is on the left side of the boundary, okay, it is nothing but equal to C naught, which is lower than C. Okay. So this is my C naught composition that is again at T equal to 0. Okay. Now what I did, I started heating the system. Then definitely the temperature increases. With the increase in the temperature, the diffusion will be facilitated and the carbon will diffuse from the carburizing medium inside your steel component. Okay. Now what happens? You just need to understand that at the surface of this boundary, okay, surface of the boundary, you can say, of the steel component, the concentration always remains constant. Okay, this is one of the condition you can say that the concentration at the boundary will always remain constant, and this will be equal to the concentration of the carburizing medium. Okay, so at this boundary, I can say that the concentration of the steel component will be equal to CS. Why is that so? Because it is in direct contact with your carburizing medium, right? So as soon as I keep my steel component inside my carburizing medium, the medium will definitely convert or will definitely increase the concentration at the boundary and it will come up to your CS concentration, right? So now what happens that this, since it is in contact with your carburizing medium, it has the concentration of your CS, but inside your steel component, the concentration is still C naught at the initial time. Okay. Now with the increase in the temperature, the diffusion from the surface or from the boundary inside the steel component takes place of the carbon. Okay. So this concentration increase basically follows such a kind of a graph that I am showing over. Okay. So from here, we'll increase the concentration of the Okay. So let me consider this, say, some X position inside your steel component. Okay. So let me consider if the carbon is diffusing from this side. So say this is my X position. Okay. This will be much closer to the boundary. The composition of the carbon will be much closer to the boundary over here, this line. But you can understand from the type. Okay. So what will happen? What are these lines basically? What you need to understand that the concentration of the carbon at your position X is increasing, right? With the increase in the temperature, more and more carbon is diffusing from the carburizing medium inside your steel component, and therefore the concentration of your steel component at my position X from the surface, it is increasing every time. Okay, so I can say that this curve is basically for your T equal to 1, the first condition. Okay, so say this is T equal to 2, and this is your T equal to 3 curve. With the increase in that temperature, that with respect to your time, the concentration at a particular position, it increases. It does not remain constant, and therefore I can say that this is a unsteady state kind of a diffusion. Okay. Now this at a particular position, as you can see, that the concentration of carbon is increasing with respect to time. So I can also means I can use my fixed second law in this condition, and I can find out what is the solution for the carburization technique to take. Okay. All right. So as we know that this is my boundary condition, and for my boundary, the concentration is remaining constant as my CS. Okay. So in your boundary condition, the initial thing that you need to understand that your X is equal to 0. That is the definition of the boundary. Okay. At a time T. Okay. So if I put this condition in my solution, what I'm going to obtain, let us see that. Okay. So C 0 comma T is equal to A plus B error function. Now your X is equal to 0, right? Under root 4D. Okay. So if your X is 0 in the numerator it is, so definitely this complete part will be equal to 0. And we know as per the definition of your error function, that is error function of anything inside, error function of 0 is nothing but equal to 0, right? So I can say that this complete portion I can equate it to equal to 0 for your boundary condition. Okay. And the concentration at the boundary, we know that this is nothing but equal to the CS. That is the concentration of the carburizing medium. Right. So from here, I can easily obtain that my A is nothing but equal to CS. Right. This is my first case or my first equation that I have. Okay. So my A is equal to CS, that is the concentration of my carburizing medium that we obtain from the boundary condition. Similarly, seeing the second condition, that is your initial condition. Condition 2 is your initial condition. As the name suggests, the initial condition is taken at your initial time, that is T equal to 0. Okay. Now, in your T equal to 0, I can take both the sides, right? If my T is equal to 0, what was my initial graph? It contains only the CS, that is the concentration of the carburizing medium. Similarly, it contains only the C0, that is the carburizing, that is the concentration of your steel component, right? So I can take X in any direction, that is X greater than 0. This is my positive side, okay, and this is my negative side. That is X greater than 0 or X less than 0 at my initial time. Okay. So for us, since we are discussing about the steel component and how the carburization is taking place in that, so I am going to take X less than 0 for the initial condition. Okay. So if T is equal to 0 and X is less than 0. Okay. So my solution X comma T is equal to A plus B error function X5 under 4D. Okay. So this is the solution. Let us find out what happens in case of your initial condition. Okay. So in case of your initial condition, when X is less than 0 and T is equal to 0. So what is the concentration in that case? For X less than 0, and t is x less than 0, and the initial time, that is t equal to 0, we mainly comes in the category of your steel component, right? And the initial composition of your steel component was basically equal to C naught, right? So the concentration will be nothing but equal to C naught, okay, is equal to A, which we have just now calculated as CS, plus B, okay? Error function. Now, since it is less than 0, but we don't know any specific value, so this will be, let us take it as x only, okay, divided by under root 4 e into c. Okay, so since 0 is present at the denominator, it is definitely going to give me a infinite value. Okay, the overall value will be infinite. Okay, now what you need to understand, that since x we have taken as a negative value, that is less than 0, so this infinite is nothing but equal to minus infinite. Okay, and as per the definition of your error function of minus infinite is nothing but equal to minus 1, right? Error function of minus infinite is nothing but equal to minus 1. So if I put up this value, this will be what? C naught is equal to Cs minus B. Okay, so from here I can say that my B is nothing but equal to Cs minus C. This is the second equation that we have. Okay, now putting up the values of A and B in the solution, we are basically going to obtain the solution for the carburization using the fixed second law. Okay, so let us put up these values and see what we are obtaining. So this is Cx comma T is equal to A plus B. This is the solution for your carburization. This is the solution for your carburization. Okay, if I further solve it, this Cx comma T is what? It basically tells us about the concentration at a particular position x with respect to your time t, right? So let me consider this concentration to be Cx. Okay, so I can take this as Cx minus Cs upon Cs minus C naught is equal to error function xy under 4d. Okay, one of the very important expression, and many questions have been asked on this one. Okay, so that is why I showed you about the derivation, that how does it take place, so that if you are getting confused with the terms that are being present over here or the order of the terms, you can understand by the derivation. You can easily remember this derivation and you can easily solve this. Okay, so this is the solution for carburization. Solution for carburization. Okay, so if you know the time of diffusion, that how much time has been provided for the diffusion to take place, what is the diffusivity value, and what is the depth of diffusion that we are considering, then we can easily calculate what will be the concentration at that particular position, right, with the help of this expression. Okay, so you can note this down and mark it as an important concept. Okay, so this is for the diffusion. How does the diffusion take place inside your carburizing medium? Okay. All right. So this is the expression that we derive. Now, since we are discussing about the carburization part, I also wanted to show you or tell you about what are the different modes of your carburization. Okay. We have seen it in one of the examples over here, that your steel component is basically being it is kept inside your carburizing medium, which is basically solid in this case, and the diffusion is taking place, right? So this is one of your solid carburization technique. Okay, so let us see different types of carburization technique that is being present inside our general concepts. Okay, so let us learn about this part, okay, and then we'll move on to the next one. Okay, so the methods of your carburization. Okay, so There are different methods. What we are basically concerned about the three methods, that is solid, liquid, and gaseous carburization. Okay, so we will be covering this. And just to give you a basic idea and understanding that how this occurs in the atmosphere is what we are going to do. Okay, so your very first method is your solid carburization. Alright. So the above example that we saw is basically based upon the solid carburization. Okay, what happens in case of your solid carburization? You take a steel component. This is my steel component. Okay, this is basically low carbon steel. Low carbon steel. Okay, and I keep it inside a carburizing medium, which is basically solid. I keep it inside a carburizing or solid carburizing. So this is my solid carburizing medium. And this solid carburizing medium is basically considered to be charcoal. This is my solid carburizing medium. Which is nothing but your charcoal, the source of carbon. Okay. So what is charcoal, by the way? It is nothing but when all the volatile materials are being removed from your food, the resultant product is basically known as the charcoal. Okay. So the steel, low carbon steel is basically kept inside your charcoal medium. Okay. And along with this, we add an energizer. We add an energizer, which is basically for this condition, it is barium carbonate, BaCO. Okay, we add an energizer, which is barium carbonate. It basically activates the diffusion. It facilitates the diffusion to take place. Okay, and if you heat the system, the diffusion of carbon from your carburizing medium inside your steel, low carbon steel, will be much facilitated in case of your solid carburization by adding of this energizer. Okay, so this is the basic concept of how this solid carburization takes place. Okay, similarly, the second method of carburization is basically your liquid carburization. Okay, now it is similar to the technique of the solid carburization. That is, we keep the low carbon steel inside a carburizing medium, which is liquid in nature. Okay, but now this liquid carburizing medium cannot be the molten carbon, right? Because the melting point of carbon is somewhat in the range of your 3500 degrees Celsius. That is a very large temperature, and it is not achievable in the atmosphere of the Earth, right? So what happens in case of your liquid carburization? Instead of taking a molten carbon, what we do, we take a cyanide solution. Okay, so you can note this now that we use cyanide solution, cyanide solution as a carburizing medium, as a carburizing medium. Okay, so what is this cyanide solution? You must have learned about the cyanide salts, right? So the cyanide solution is nothing but a composition of carbon and nitrogen. Okay, so it can be basically being converted into the nascent carbon and the nascent hydrogen, which are released in your electrons. Okay, so this is your cyanide solution, and it can be broken down into your nascent carbon and nascent nitrogen. Both of these are being absorbed over the surface of my low carbon steel, thereby increasing the strength of the surface. Okay, now what you need to understand that your carbon and nitrogen both acts as what you say the pinning positions for the dislocation movement, right? Your carbon along with your nitrogen both pin down the dislocation movement and therefore increases the surface hardness. Okay, so there is an additional factor of nitrogen which can also enhance the strength of the surface. Okay, so that is why we use a cyanide solution instead of any other solution. Okay, so they are being absorbed over the surface. If I just draw the diagram, it is much clearer. Okay, this is my cyanide solution, and this is my low carbon steel. Okay, so this is my low carbon steel block. So carburization is to be carried out, and this is my cyanide solution. Okay, so in this case, the nascent carbon and the nascent nitrogen both are being going to absorbed over the surface of my steel. Now, what do you mean by absorption? Please remember, not the absorption, but absorption takes place in this case. Absorption. Absorption occurs at the surface. Right? So, what is this absorption? Absorption is nothing but it is a chemically reacted system. Okay, when the surface over the surface, what happens that with the presence of your carbon and nascent nitrogen over the surface, it gets chemically activated. Okay, a chemical reaction. In simpler terms, you can say that a chemical reaction takes place over the surface. Thereby, the carbon and nitrogen gets absorbed inside the surface of your steel compound, and thereby increases the surface height. Okay, so what is absorption? In absorption, simple carbon and nitrogen could have been absorbed inside the carburizing, the steel component without any chemical reaction. Okay, but in case of your adsorption, the chemical reaction occurs at the surface, thereby it binds the carbon and nitrogen over the surface. Okay, so this is the basic difference between your absorption and adsorption. Okay, so again, you need to heat the system. Definitely, you need to heat the system for the reaction to take place or the diffusion to take place. Okay, so this is how the liquid carburization technique works. Similarly, moving to the third concept or the third method, that is the gaseous carburization. Okay, now again the concept is same. In case of your gaseous carburization, again you have a low carbon steel block. It is kept inside a chamber, okay, which is filled with hydrocarbons. Hydrocarbons like your methane. The most common example is of your methane. Okay, so this is my low carbon steel. This is the hydrocarbon medium. Hydrocarbon medium. For example, you can write your methane. What is methane? It is nothing but your CH4. Right? Now, if I heat the system, what will happen? Since the methane can be broken down into carbon and hydrogen, CH4 can be easily broken down into nascent carbon and hydrogen. Right? And this, since they are in the gaseous form, it is free to move throughout the surface. Right? It is free to move throughout the container or whatever the carburizing medium is kept inside. Okay, so it is easily able to move throughout the container, and therefore it can easily get absorbed over the surface. Okay, so the low carbon steel on heating this complete system, the carbon will start getting absorbed over the surface, thereby increasing this strength. Okay, now please remember, in this case, even hydrogen get absorbed, but it does not has a very significant effect over the surface area, mainly because of the small size of small size of hydrogen. It does not pin down the dislocation damage. Okay, so the major element that is responsible for your gaseous carburization to increase the surface hardness is your carbon. Okay, so this is the basic concept behind your gaseous carburization. Okay. Now, there are many advantages of your gaseous carburization as compared to the other techniques. That is the solid carburization and your liquid carburization respectively. Okay. And you, as you can see that you can easily analyze what are these advantages. First of all, since it is present in the gaseous state, so the diffusivity rate will be much higher. Okay. The diffusivity of your gaseous component is much higher as compared to your liquid, which is even much higher as compared to your solid state, right? So diffusivity is higher in your gaseous state as compared to any other state of matter. Okay, so you can say that this is your fast process. This is your fast process. The advantages I am talking about. The advantages of your gaseous carburization is that it is a fast process. Okay, and why is that so? Because the diffusivity of your gaseous is larger as compared to your liquid, which is larger as compared to the solid state. Okay, so this is definitely a fast process. Along with this, the other advantages is that it can be used for your bulk sample. Okay, so in case of your liquid and solid containers, it is limited to the amount which it is limited to the amount of the carburizing medium, right? But in this case, it can be used for your bulk sample. Can be used for your bulk sample. Okay. All right. Along with this, uh, gaseous carburization is actually very easy to control. Okay. Now, why is that so? Basically, with the changes in the pressure using the Lee-Chatelier principle, I can basically analyze what will be the carburizing medium, what will be the rate of carburization, right? If I adjust my pressure, I can basically increase the carburizing, I can increase the amount of carburization that is taking place. Thereby, I can increase the surface hardness of the steel component. Okay, so it is much easy to control. We will be seeing about the Lee-Chatelier principle ahead of this. Okay, just to give you a basic understanding, what happens is that with the changes in the pressure, we can adjust the rate of the reactor to take place. Okay, so we can say that easy to control. Okay, so these are some basic advantages of your gaseous carburization as compared to the other. Okay, so this is all about the carburization part. Now, let us move on to the next concept, that is your decarburization. Let us see what happens in case of your decarburization.